We're
Okay.
recording.
All right. Thank you, George. Well, good evening, everyone, and welcome once again to Amateur Astronomers Incorporated, also known as AAI. And AAI makes its home at William Miller Sperry Observatory on the campus of Union County College in Cranford. Now, since the observatory is closed at this time, we are continuing with to hold these presentations online and on Facebook. Now, on the third Friday of each month, from September to April, we hold our monthly meetings, which include guest speakers from educational institutions around the country. And consequently, tonight, our monthly meeting, and our speaker is Dr. Matt Orr. Dr. Orr is a postdoctoral scholar. Unfortunately, I can't read this here. I'm sorry, postdoctoral scholar in theoretical astrophysics. Jointly at Rutgers University and the Center for Computational Astrophysics at the Flatiron Institute in New York City. He completed his doctorate at Caltech in 2019, having studied galaxy evolution and star formation in cosmological zoom-in simulations. He also received his undergraduate degree in physics from University of Southern California. I'm having a hard time reading in the dark here. Okay. The title of his presentations is Galaxies Aren't Great at Making Stars. And with that, Matt, I'm going to turn this over to you.
Right. Well, thank you very much for the introduction, and I'm excited to be here. So yeah, I'm Matt Orr. I'm a joint postdoc between those two fine institutions, which means I ride NJ Transit up and down the Northeast Corridor all the time, which is sometimes a blessing and often a curse. Anyways, I'm new here, so I'm getting used to riding trains as opposed to using freeways. Anyways, I'm here and very excited to share my thoughts and some fun facts about galaxies and their ability to make stars and why they're frankly really crappy at it. So without further ado, we're going to learn about star formation today. So although I do have a telescope, I've been trying to take fun pictures with it. I haven't taken enough pictures to replace all the beautiful NASA astronomy pictures of the day that I just threw in here. So you're gonna have to make do with other people's fine photos as opposed to either my own, or had I known well about it or found like your guys' archive, I could put some of your guys' photos up here, which would have been a fun surprise. But anyways, we're going to talk about star formation today. Where does it happen? Why does it happen? Sort of what sets the scene? I'm going to sort of offhandedly just talk about some of the physical processes at play and give us an idea of sort of everything that's going on in galaxies in terms of star formation. So sort of tautological in some sense, but stars form in galaxies. After all, there's some fun pictures tonight, and I've seen plenty of wonderful, beautiful pictures of star-forming galaxies where you see beautiful swirls in H-alpha and the UV if you're looking through Hubble or something, and soon we'll have James Webb looking in the IR. But oftentimes when you go and look out at these galaxies, you see the beautiful blue light from them. That's the blue light from the young massive stars that are just forming, or cosmologically speaking, just forming. So what are galaxies? Great question. We might wonder to ourselves, are they the swirls of gas? Are they the dark matter halos? Are they the stars? Well, oftentimes I think we ought to say galaxies are just a bunch of stars. Because if you go and look at some fun old-timey dictionary, that's all they really are. They're a bunch of stars. In fact, in like the 20s, before we actually knew what galaxies were, you would say that a room has a galaxy of people in it. It's a bunch of bright individuals, which is a fun, weird, archaic definition. But there's a lot of other stuff, and that other stuff is where I think all the fun is. I'm not a stellar astrophysicist. I'm much more interested in the interstellar medium and the physics of feedback from massive, feedback from stars, but more its effects on gas rather than the stars themselves. So the key point is galaxies have gas. It's the fuel for star formation. It's the beautiful emitting and absorbing material that we see in H-alpha and oxygen, other optical tracers that you might go out and look at in your backyard telescopes or the fine observatory in your own backyard. And you'll have to go to space for some of the other tracers. If you want IR, you got to go to space, or at least fly in Sophia up at 40,000 feet or so above all the water vapor. So galaxies have gas, and of course, there's also dark matter. Frankly, I actually don't really care what dark matter is. Sort of funnily enough, as a theorist who works on galaxy formation and evolution, the model that dark matter is heavy and it's there is about all I need to get galaxies mostly right. So, you know, other astronomers might find that apocryphal, or at least maybe a little flippant. But I would say, no, I don't care what dark matter is. It's stuff, and it's heavy. And of course, there's planets. We're on one. Earth is cool. I'm, again, not an exoplanets person. Those people, you know, that's a hot field right now, and hopefully you've either had someone who works on exoplanets come talk to you, or will have one in the future. There's a lot of really interesting stuff going on these days with exoplanets, and of course James Webb is going to be looking at them as well. But as far as planets go, pretty much just Earth. Mars is cool, but I'm an Earth guy. So again, the defining feature of galaxies, though, are if they're stars. And when we look out in the universe, we see a whole panoply of galaxies. You know, there are various morphologies, masses, many shapes, sizes. Are they star forming? Are they not? You know, in this one photo, we have, you know, a number of morphologies and masses. We see a massive elliptical in the foreground, a spiral galaxy that is, I believe, actually associated with it on the sky, and then a background spiral and a star, a couple of stars in the frame. You can see the diffraction spikes. But the key takeaway is there isn't one definition of a galaxy. There isn't one kind of galaxy. Rather, there are many kinds, and their sizes and shapes tell us a lot about them and what's going on in them and what their ultimate fates will be. So again, depends on how massive they are. The Milky Way is, I think there's something like 10 to the 10 stellar masses of stars in the Milky Way. The whole halo of the Milky Way is about 10 to the 12 solar masses in terms of the dark matter plus the stars plus the gas. So one of the first questions you might ask about galaxies, and when we try to think about what's going on in galaxies, is there a relationship between the number of galaxies and how big those galaxies are? You know, some function that tells us about the mass of galaxies and how many there are. In fact, there is something, it's called the galaxy mass function, and you could go to the literature or you know, go to the, I think this was an astrophysical journal paper from 2009, which I believe is open source now. So all the aperture is open source now, which is great. But on the x-axis, we have the mass of galaxies, so how big are the galaxies? And the y-axis, we have the number of galaxies we see per unit volume of the universe. And then the red line is what we see out when we go try to count up the number of galaxies we have. Modulo uncertainties about did we find all of them, etc. And the Milky Way, very interestingly, lives in terms of, and again, the x-axis is actually stellar mass. But the Milky Way is really interesting because we live right at this sort of kink in the curve where we're right at the end of where most galaxies are. And then there's this rapid drop off where there's a lot of galaxies that are less massive than the Milky Way. There aren't that many galaxies that are a lot more massive than the Milky Way. And that's an interesting in its own right. And furthermore, when we go and look at what those small galaxies are, we just, you know, take some kind of census, we see immediately that galaxies, the Milky Way mass, and smaller generally, although if you get down to the really faint end, the really tiny ones, those are kind of done doing it. But the sort of the Magellanic Clouds, the Milky Way, things in that range are all still making stars. They're not done yet. They're bright in H alpha. They are bright in the UV often, etc. And you know, these are most of the galaxies in the universe. You know, they're not exploding with star formation like they once were. There was more star formation in the past than there is today. But galaxies less massive than the Milky Way are still making stars. And then on the other end, things much bigger than the Milky Way seem to be mostly all done making stars. You know, there's a few exceptions here and there, and those things are really interesting to me. There are things out there. There are super spiral galaxies that are 10 to 50 times bigger than our own Milky Way that are just big spirals that didn't get the memo to stop making stars, and in fact, just giant, beautiful, big spirals. That's a secret passion of mine. But for the most part, they're big elliptical galaxies that are red and dead, as people might call them. And so there's this dichotomy above and below the Milky Way. So it's fun that we live right at sort of the threshold of this, of where star formation seems to kick off. And then so we might start to ask ourselves, well, why is this? Is there a hand-wavy explanation? And I'll argue, yes, there is a hand-wavy explanation. Namely, galaxies that are less massive than the Milky Way live in sort of regions of the universe where gas continues to fall into them. They're still being actively fueled, and material is still accumulating, and that material is still falling in, cooling off, getting dense, and turning into stars. And that alone explains at the very least why they continue to form stars, because if left to their own devices, a galaxy will run out of gas, and I'll show this later, in about 1 billion years or so. So every billion years, you got to have a new delivery of fuel to keep your star factory running. Now, galaxies, though, that are much bigger than the Milky Way seem to form by smashing together smaller galaxies. So you knock together a couple of nice spirally disky galaxies, and generally speaking, their angular momentum vectors don't line up. So as opposed to adding 2 disks and getting a bigger disk, you add 2 disks together and you get a mess. And importantly, usually it also messes up the gas reservoir. And so when that happens, well, it sort of kills star formation, and any residual gas is hot and unable to cool off and collapse into stars. And so the interesting thing is that the Milky Way lives right at the edge of this point where it's kind of grown as much as it can from just making stars. That gas has fallen in, and it's one of the biggest ones that's been able to grow by just making stars. Galaxies much bigger than the Milky Way grow by eating smaller galaxies, for lack of more precise language. And generally, we find them in galaxy clusters, the centers of galaxy clusters, where things are falling in together, as opposed to just gas falling into them. So because this is a talk about star formation, let's talk about the small ones, the small star-forming galaxies that we know and love. So what's going on in these star-forming galaxies? Why are they star-forming? Is there something special about them? Again, is it simply a property of material falling into them? Is it their mass alone? Is it the kind of gas that falls into it, etc.? So let me give you the simplest recipe I could come up with as a theorist for how you make stars. Now, flippantly, you take stuff and they collapse into stars. Gravity makes stuff dense. You run out of thermal support. You have hot gas. That hot gas cools off, again, through beautiful tracers that you might see in a telescope like H-alpha or oxygen-1 or ionized carbon. These are all things that, since we see them, it's photons running away from this gas. And when that happens, it's taking the energy away and thus cooling it off. And as it cools off, it gets denser. And eventually that density means that gravity wins and it turns into stars. Again, that's being a little short with the story. And there's a ton of fun astrophysics that you can either make a career out of or at least go get a PhD in. But there you go. That's how we do it. But again, okay, you're right. It's messier than that. There's something that I've completely left out. Namely, it's the fact that young stars explode. That's why we have these beautiful nebulae that we see. The reflection nebula, where we see the ionizing photons that are lighting up the clouds and things like that, and the supernova remnants. That young stars are blowing winds and they're stirring up the gas. They're heating up the gas in their locales. Or on average in the galaxy, it's sort of heating gas everywhere. There's the average interstellar radiation field. It's also a heating source for gas in the galaxy. And so, broadly speaking, we collect all of this and call it feedback, or stellar feedback if you're being a little more specific, because for people who care about big galaxies or just black holes in general, there's also galactic nuclei, and the physics of accretion on those do something. But I'm not going to talk about that because I didn't get a PhD in it. So we're just going to talk about stellar feedback, the fun things that stellar feedback does, and how we kind of, think about that in terms of star formation efficiency. So if let's say each of us in the room is an atom in the ISM, we might find ourselves somewhere in this life cycle, and I'd like to call it the gas cycle. Now, some of you in the room might remember in 3rd grade or something like that you learned about the water cycle and how water moves around on Earth and moves through different phases. And I would say that the ISM, the interstellar medium, and atoms and molecules in our own galaxy and other galaxies do much the same thing. So you might imagine that you're an atom living in some blob of gas. Now, if you're just sitting there doing nothing except radiating your energy away, well, eventually gravity is going to start winning as you cool off and lose your support against gravity. So you start collapsing and fragmenting, and you start getting, dense, opaque clouds that you might see as Bach globules or something like that. And as they get colder and denser, that's when we get the fun. You get towards molecules that you're not going to see in your backyard. You're going to see complex organic molecules like HCN or CO or something like this that you might have to go to a radio observatory to see. But they're there, I assure you. It's not just dust that you're going to see. And then eventually you're going to make stars, because all that stuff eventually then finally collapses down into stars, into the photosphere of stars. And at this point, there's a fun thing that happens. Namely, you've made stars. And so once you've made stars, well, those stars are going to start messing up their homes. You know, it's like a toddler, you know, it's going to tear holes in your walls and, you know, get in your car and drive it into the garage, whatever kids do. I don't have kids. So feedback happens and you start breaking up your clouds. You start dispersing the material that's been gathered. And really, these stars ruin it for everyone else. Rather than being able to turn all of that stuff into stars, you only get to turn a little bit of it into stars. Because the first couple of stars that form start blowing the cloud apart. And it does so pretty rapidly. Now, if you wait around long enough, or a spiral arm comes by, or two clouds smack together, or a dwarf galaxy comes in or something, you're going to reassemble that material, the material that's been diffused by, you know, radiation pressure, stellar winds, supernova explosions, all that. You'll reform it into clouds, or you'll rebuild dense structures. And you could imagine then that this process all starts over again. Now, again, things are never quite as simple as this, but broadly speaking, I'd say that this kind of gives you an idea of what's going on. Now, the cloud formation or the star formation and cloud destruction process, you know, it's a little up in the air still of how long, what this time scale actually is. But we reasonably believe that it's somewhere on the order of 20 to 100 million years. That once you get sort of into the phase of collapse, it's only a couple of free fall times until you make stars. And so if you have a cloud that's, you know, one of these large molecular clouds that we might see, something like Taurus or what was Orion or something like this, well, you know, you give it 50 million years or so, and maybe it's not doing anything. But then as soon as it kind of reaches this threshold where it starts collapsing, well, the show runs pretty quickly. And in only, you know, maybe 10 million years or so, you're making stars. In only 5 million years or so, you're done making stars and you're blowing the cloud apart. And so, you know, somewhere in this range is the lifetime of clouds and the sort of the star formation phase. Then there's also this quiescent phase, which is the reassembling of material. It's the off phase. If you have an on-off cycle, or, you know, it's the downstroke in an engine or something, or the upstroke. One of the strokes in your diesel engine, it's the other one, the one that isn't getting the power out. It's been a while since I took a thermo class. Anyways, so when we try to think about this, we realize that, well, if we add together this and we say that clouds take about as long to form as they do to assemble and collapse and explode, well, this ends up being about as long as it takes for, if you're in the Milky Way, you to orbit the center of it once. So once per orbital time, this picture is kind of going on. You can imagine that this is about the expected rate of star formation. One of these events is happening per orbit. And so if every time we have these clouds making only a little bit, or taking only a little bit of the material and turning it into stars before they explode, rip themselves apart, well then only a fraction of the gas per orbit is being turned into stars. And so you can imagine this is where I got my title from somehow, that galaxies aren't great at making stars, because, well, if I gave you 200 million years to do something, you'd probably get a lot done. Whereas galaxies are only turning, you know, 1 to 3% of their stuff into stars. It's their one job to turn stuff into stars per 200 million years. And so if we adopt this definition, which broadly speaking is how we might want to talk about the efficiency of star formation, well, then every orbit, which for the Milky Way, for us out here, it's, you know, 200 million years or something is about our dynamical time. We're turning only a small fraction of the gas in the solar circle into stars. And so if out at the solar circle, the mean sort of density of gas is, what's the surface density out here? It's like 30 solar masses per square parsec. That sounds like a lot. It's 30 suns, but a parsec is pretty big, and a square parsec is even bigger. You know, you're only turning every 200 million years. That means out at the Milky Way, in the Milky Way out by where we are, you're getting 0.3 solar masses per square parsec. So we're making, you know, a red dwarf or two on average, of course, per orbit out here, per sort of our volume. So you can imagine that there's not a lot of star formation going on in our part of the Milky Way. Now, if you look in towards the center, there's a lot more stuff, and there's a lot more stuff going on. So that's why the central molecular zone is exploding, and or not exploding right now, but will probably be exploding soon, et cetera. So how do we tell if this is happening? What tracers do we look for when we try to quantify this in some either observational sense or at least theoretical sense? And so, like, how many stars do we actually make? What's the scaling relation we might go out and measure? This is really what I studied in my PhD. It's something called the Schmitt relation. So I'm gonna throw another plot at you guys because plots are fun. And this is a really fun one, I think, because this is a scaling relation where we plot the mass of gas in galaxies versus the amount of star formation happening in them. And the best part about it is it's a empirical physical law that's named after two people, Kennickett and Schmitt, Rob Kennickett and Martin Schmitt. The best part is they're both still alive. That's rare. Martin Schmitt, especially, it's kind of surprising because he was the guy who discovered quasars back in like the 50s, and he had this cover of Time magazine in 1966, which I just think is really fun because it's like the greatest like Time magazine cover of an astronomer I've ever seen. Like Einstein's holds nothing to this because it's like the $6 million man kind of thing. And when I was at Caltech, he's still around. He's emeritus, but he would go to lunch every day at the Athenaeum with his friends, and you see him, and you're like, man, that guy's really tall, and he figured out star formation in the 50s. So, anyways, we're going to talk about the Kennickett-Schmitt relation for a little bit. So, really, what this boils down to is a way of trying to quantify and see whether or not what I told you before was lies or not. Are we bad at making stars or not? So what we have here, again, on the x-axis, now I've fudged it a little bit, it's the surface density of gas, but whatever, it's the amount of gas that we have in part of the galaxy. And the y-axis, it's the rate of star formation. So the real units on it are the solar masses per year per square kiloparsec. Now, what we see on here is there's a couple of dotted lines that are running across it where it's per orbital time, what's the efficiency? So we see there's 1, 10, 100% per orbital time. And there's maybe 2 points that are, a couple of points that are right up there, like 100%. But what you got to take away is more gas to the right, more new stars. But they kind of run together. So for the efficiencies are staying the same in some sense. But regardless, for most of galaxies, most of parts of galaxies, it's a few percent efficiency. Which I wrote this joke before thinking about the lockout too much, but it's worse than a lot of like pitchers' batting averages. You're not really voting on your pitcher to do any work, and these galaxies are even worse than that. So whether or not they'd get a contract, I don't know. Anyways, so we can see that at the low surface density end, the low mass end, where there isn't a lot of stuff, galaxies seem like they're really, really bad at making stars. Now, getting into it a little bit, part of this is because the material really isn't very dense. There's a lot of diffuse, hot gas out there. When you're looking at these galaxies, you might see some of these more ionized material. In general, there isn't a lot of molecular gas out there. There's not a lot of dust and things that help it cool off, and so they get really bad at making stars. Very, very bad. And then in the middle, sort of I call this the bread and butter section of galaxies, they're kind of bad at making stars. It's a few percent efficiency to 10% efficiency per orbital time. So the Milky Way, a lot of it lives sort of right around here. The solar circle lives around here as well. And then as you get towards the centers of galaxies, it's much better. Seemingly, some centers of galaxies might be almost 100% efficient. At every orbital time, as quickly as you can pour gas into the centers of galaxies, it turns into stars. Now, there's a caveat here, maybe. It's kind of hard to tell how much gas is in the centers of galaxies for a lot of reasons. Namely, it's a small area. There's a lot of obscuration. It's unclear if our methods of guessing from the amount of light we see, the amount of mass, if they work the same in the centers as they do in the outskirts. So I'll put better maybe on there. But it still gives you an idea that as you get more dense, things improve somewhat. We're pretty sure of that. But this whole thing is just to mostly say that galaxies are terrible at making stars, and it's related in many senses to the kind of gas that you have. That in the outskirts, it's hot. It's gravity has a hard time pulling it together. There isn't a lot of stuff helping it cool off. And then in the centers, there's just too much stuff. Gravity always wins. You can't have supernova go off fast enough to stabilize the material. And that in and of itself is, I think, a really cool thing. And so if we again are to try to quantify where this is happening, or just give you an idea, again, the centers of galaxies generally are in this very high gas mass regime. The sort of mid-range, the disky parts, the nice fun parts of galaxies are sort of in the middle. And then the far outskirts are really, really bad. And so the Milky Way, where we would be, is we're 8 kiloparsecs or so out. We're sort of in the edge of the nice fun disk part and getting towards the outskirts. It's one of the only things I guess I really don't like about living in the northern hemisphere, is that the Milky Way is a lot worse here than in the southern hemisphere, because we're looking out of the galaxy as opposed to into the galaxy. So it's not quite as bright. But that gives us an idea that we're not really in the center of things, because otherwise it might look pretty similar in both directions. So I have to apologize. Namely, I'm going off of a PDF here as opposed to my laptop. So all of my animations for the next 3 slides don't work. So I'm going to give you this picture, and we're going to imagine that it's a simulated galaxy whose gas is going in a cool orbit, and we get to watch it for like 2 giga-years, and I'll like point out as merging galaxy comes in and stuff. And it would have been a great time. So instead, I'm just going to tell you about the kind of work that I do in brief. And perhaps I shall, in the next research note, be able to send around a movie or something that you can share with folks. But I work with the FIRE simulations, the feedback in realistic environments. It's a suite of cosmological zoom-in simulations. So you might have seen some videos of simulations where you simulate the entire universe and you see a bunch of galaxies doing stuff. We don't do that because all those galaxies are like 4 pixels and they don't have a lot of physics in them, or rather you paint on things like the Koenig-Schmitt relation. You say, well, those galaxies have to work this way. Whereas we focus in on one galaxy at a time, or one galaxy and it's the things that will fall into it by today. So you have things like the Magellanic Clouds and such that will fall into it. We simulate those as well. And we try to see why things like the Milky Way, why things like the Magellanic Clouds, how and why they form. And so we simulate those at very high resolution, and we try to put in the minimal amount of physics to get things right. Put in gravity, we put in gas cooling, we put in some rules about how dense gas turns into stars. And then on the back end, we get out things like Koenig-Schmitt, which is cool. So here's another video that won't work. It's looking at how one of these galaxies evolves from redshift 30 down to today. The right side would have been gas colored in weird colors that my advisor chose. And the left would be in stars, and it would look like Hubble, and it would look really cool. Ooh, fun times. And then this one was also going to be a video of looking at how Koenig-Schmitt evolved. But what we have here is one of these simulated galaxies. And on the left side, it's a Milky Way-like galaxy. This is about a giga-year ago. Is it a giga-year ago? It's a while ago. And on the left, we have the gas, and you can see the big swirl of gas, and you can kind of see spiral arms. We don't have, in this galaxy, there aren't really strong spiral arms like M51 or something. It's more of a flocculent galaxy, so it's something more like NGC 7331 or the Sombrero Galaxy or something. There's nice flocculent arms as opposed to strong spirals. And then in the middle panel, we have some estimate of where new stars are forming in this galaxy. You can see they roughly follow the gas. And in the right panel, I've made up a cruddy plot that should be animated of pixel by pixel what Koenig-Schmitt looks like in this galaxy. And then I drew kind of a blob around Koenig-Schmitt, copy pasted it. I was like, oh, that's where the observations are. And it's really cool that we can now today, with supercomputers and grad students not being paid very much, run simulations of galaxies, of Milky Way-like galaxies, and we reproduce the physics that make galaxies cruddy at making stars. That with supernova explosions, with stellar winds and photoionization, we cool and heat the gas in such a way that, well, we don't make very many stars. This was a huge issue in simulated galaxies up until about 2014 or so. Around then, there was a big turning point where we finally had the resolution, we finally had the physics to be able to do this, whereas before, we just would simulate a galaxy, all the stuff would fall into it from the intergalactic medium, and then, well, it all just turned into stars, and we have dense nuggets, and the simulation would crash because it got too dense, and it didn't look real anyways, and so we said, okay, well, we'll start over with a different kind of simulation. So eventually, finally, we've been able to do this, and this is really the one of the centerpieces of what I did in grad school. Now I look at sort of the intricate physics of supernova themselves, but anyways, I guess I didn't time this very well. Anyways, just remember that here's some takeaways. The simulations would have taken a little longer to show. I'll go with that. Galaxies really at their core are just big star factories. Their entire goal is to process hot gas from the IGM into stars. And they're supposed to do that forever, and they will do that forever. In the time since around redshift 2, so in the last 8 gigayears or so, the rate of star formation has been falling. Part of that is just the density of gas in the universe is being converted into stars. But galaxies are big star factories that are constantly punching all the cold gas and keeping it from collapsing, and are heating it up, not necessarily ionizing all the cold gas, destroying the molecules, definitely shoving it around and keeping them from collapsing. And they're terrible at making stars, in summary. So with that, I'll say thank you. I'd love to answer questions because I think I talked fast and it's been a long day. So I would love to answer questions, talk about simulations, talk about supernova explosions, the clustering of supernova, anything you want to ask me. I'm here for it.
Thank you, Matt. Let's start with, does anybody here in the audience have any questions? Yeah. Hold on, I have to come to you. Let me start with Cliff, John, and then I'll come to you.
My question is relates to dark matter. How can you ignore it? It has, in addition to its mass, it has another property which is kind of a dot property. It cannot get rid of its momentum by frictional, radiative, or any other kind of process. So it just hangs around being rapidly moving heavy stuff with lots of momentum. And I would think this would influence the behavior of the regular matter that's trying to form stars.
Go back and forth. So that is correct. All of that is correct. And we do include dark matter, but all it is additional collisionless particles that are thus unable to, except through gravitational n-body interactions, interact with the rest of the material. So we include a dark matter component that is, we started out, because the simulation started redshift of about 100 or so, some of the early perturbations of the early universe, and thus collapsing into the halos that will make things like the Milky Way. And so one of the very interesting things is, at early times especially, when there's a high ratio of regular matter to dark matter in these halos, baryonic physics can strongly affect the shape of the dark matter halo. Because as supernovae go off and expel gas, and they change the shape of the gravitational potential that the dark matter itself is also living in and coupled to, it'll help kind of shape and smooth out the dark matter halo. And so we do include it. It is important, and it's really interesting to look at how the baryonic physics affect the dark matter halo. And in fact, this additional supernova and these kind of physics have helped us understand some of the early problems with dark matter simulations, where before, because we would say, okay, if we just had dark matter and just had gravity, well, everything collapses and you make big halos for big galaxies, but around those big halos are smaller halos for smaller galaxies, and around those smaller ones, or yet smaller ones, there's kind of a turtles all the way down problem. And so we had the missing satellites problem was what it was called, where we just had, simulations said there should be way more galaxies out there than we see, or way more dwarf galaxies around big galaxies, or satellite galaxies around big galaxies. And with the advent of putting in the additional baryonic physics, we understand this sort of subtle interaction between when you are shoving around the stuff that we know and love, the stars and gas, it smears out the dark matter distribution in a way that gets rid of a lot of the smallest scale structure and sort of helps alleviate this missing satellites problem. So it is important, but it's, again, I will stand and I will die on the hill and say it's important insofar as it has mass and it interacts with gravitationally. If the dark sector has a bunch of other interesting physics, I've yet to see that it matters. So hopefully that answered some of your question.
John, did you have a question?
Yes. I'm not sure if I understood right, but it seemed like the diagram, I forget the man's name that goes with Schmitt, but that diagram was showing higher efficiency of towards the center of galaxies. Is that right?
Essentially.
But if you look at like the images, right, the star formation always seems to be in the outer parts of the galaxies, right? If you look at a picture of like M51 or something.
So it's very difficult in terms of if you're looking at tracers. Sorry about this.
Sorry.
It's very difficult to just pull out, like if you just pull out a raw H alpha image of M51, say, and just say, okay, this is going to tell us the star formation rate. Because the centers of galaxies have, again, they have a lot of material, they have a lot of dust. And so there's a ton of attenuation and embedded star formation in the centers of galaxies. And so for the most part, the estimates that we have for star formation there have to be a combination of some UV, some H alpha, but also longer wavelength reprocessed infrared light, like 24 micron light. And so this is the deeply embedded star formation that's otherwise obscured in the centers of galaxies. And so you're right that just on the face of it, if you were just to try to estimate from the ultraviolet light or the H2 regions, that it doesn't look like there's a lot in the center, but there's a lot going on. It's just obscured by dust. So dust is also important. Dust is what keeps other people up at night, observers.
Other questions here? Okay. Bring it to Mary Lou. Okay, Mary Lou, hold on.
Steps in for the night.
So I have a question about the supermassive black holes in the centers of galaxies.
Mhm.
In your simulations, do they come naturally?
Right. So in this simulation, we don't include the supermassive black holes. This specifically was the Fire 2 simulation, so the second generation of them. But now we have Fire 3, where we are including the supermassive black holes. But one of the things that I carefully danced around was saying that for the most part, we're simulating Milky Way mass and lighter galaxies. The effects of supermassive black holes and accretion onto them and the jets they produce, and if you're looking at M81 or something like this with a beautiful supermassive black hole in the center that is accreting material, for the most part, the effects on the galaxy don't become much sort of the dominant effect on the galaxy until much above the Milky Way. And so we kind of got away with not including them in our galaxies, although now we're trying to include them because we want to simulate the larger halos.